welcome to our first online colloquia. As you can see, we have a lot of things to figure out and we're working on it, and I appreciate your patience. So, with that, I'd like to introduce today's speaker, Dr. Nevin Weinberg, a professor of physics at the Kavli Institute for Astrophysics and Space Research at the Massachusetts Institute of Technology. Professor Weinberg earned his BA in physics from the University of Chicago in the year 2000, his PhD from the California Institute of Technology in 2005. He has been a postdoctoral fellow at the Kavli Institute for Theoretical Astrophysics at MIT and at the University of California at Berkeley, before joining on at MIT in 2011, where he has been a professor since, and he's now currently an associate professor. Professor Weinberg is an astrophysicist, a theorist whose research interests include compact objects, binary evolution, stellar oscillations, explosive thermonuclear burning, and currently short-period binary systems, including stellar binaries, planetary systems, and compact object binaries. He is the author or co-author of over 50 publications. In 2018, he was the recipient of the MIT Buckner Faculty Award for undergraduate advising, and today he'll be speaking on When Stars Go Nonlinear, Large Amplitude Tides, and Stellar Observations. So with that, I'm going to throw the ball over to Dr. Weinberg. If you could share your screen, I will put up both your slides and your face.
And thank you very much for the invitation, the virtual visit. I've really been enjoying it. This picture that I guess you guys have been looking at for some time now because of these technical difficulties. This is a photograph of Jupiter's moon Io, taken by Voyager 1 as it passed near Jupiter in 1979. And so Io is in a slightly eccentric orbit, which means that it experiences a time-dependent compression and rarefaction as it propagates around Jupiter, as it orbits Jupiter. And that compression and rarefaction leads to a heating of Io's interior. And as a result, Io is the most geologically active body in the solar system, despite its small size and its age. And so you can see a nice illustration of that geological activity in this volcanic plume spewing out the top of this image here. And I guess my pointer with my mouse doesn't work either, so I can't really point at it, but you can probably see it. And so in this talk, I'm going to be describing tides in completely fluid bodies, not solid objects like Io. But I like this example because I think it nicely illustrates an important theme of our work, which is that tides can sometimes have a really dramatic impact on a binary and its components. And so let me just start by acknowledging my collaborators, and especially the students that have worked with me at MIT and have gone on to graduate and are now postdocs at various places. So Keaton Burns, Reed Estick, and Hong Yu. And so you'll see their names sprinkled throughout the talk in the various papers that we've written together. So tides are important in really a wide variety of binary systems. So they're important in exoplanet systems, especially short period exoplanet systems, where they can impact the formation and survival of these exoplanets. They're important in stellar binaries. So there are examples of binaries called solar binaries, where you have two sun-like stars that can sometimes be in very short period orbits, a few days, and in an eccentric orbit. And in time, the tides will circularize those orbits and spin up the stars. Didn't realize that, so I imagine no one was seeing any of these slides I was talking about. Is that right? Okay, I'll just talk about the Earth and the Moon. So the Earth and the Moon, have a spin-orbit coupling, and the tidal bulge of the Earth is leading the Moon's orbit. So hot Jupiter. So these are another interesting system where tides are important. These are objects in which you have a Jupiter mass planet in a few-day orbit, 2 or 3 day orbit. We know of something like 100 or so of these systems. And last year's Nobel Prize in Physics, half of it went to two astronomers who made the first detection of a planet around a sun-like star outside of our solar system. That planet was a hot Jupiter. So hot Jupiters are kind of Nobel Prize-worthy objects. And so if you think about the tides in these systems, the planet is sort of opposite the Earth and the Moon. The planet orbits much faster than a typical star will spin. So a star like our sun has a spin period of sort of 25, 26 days, whereas the planet's orbiting in 2 or 3 days. And so the tidal bulge of the star is lagging the planet's orbit. And so the direction of the torques are opposite the Earth and the Moon. And so the star is getting spun up, and the planet is losing angular momentum. So it's in-spiraling into the star. And so one of the, this is something that people understood when they first detected hot Jupiters in the 90s. And, one of the questions that's been around since then is what's the rate at which these planets are falling into their host star? To answer that, you need to know the efficiency of tidal dissipation. Essentially, what's the viscosity of the star? And so in a little bit, I'll be talking about work that my graduate student and I did to address that problem. What's the in-spiral rate of hot Jupiters? And that's important for understanding their survival and information. Okay, and so how do you study these systems? So the sort of standard approach is to use what I like to call tidal perturbation theory. So the idea is if you take a spherical star and you put a companion near it, it distorts the companion, makes it sort of an ellipsoidal shape. And the amplitude of that distortion, delta R over R, is proportional to the ratio of the masses of the companion to the star times the ratio of the radius of the star to its separation cubed. And so now if you think about the fluid forces are inherently nonlinear. And if you put a perturbation into those fluid forces, you can sort of get a Taylor series expansion in delta R over R. The restoring force has a term that's linear in delta R over R and quadratic and cubic nonlinear in delta R over R. And so the sort of typical approach that people have taken is to just ignore the nonlinear terms and just keep the linear terms, what you might call linear tidal theory. And there really isn't any good argument for why you would do this, except that it makes things simpler. That when you include these nonlinear effects, things get more complicated, and it's a lot easier to study tides when you just drop those nonlinear terms and just keep the linear ones. But what I'll show is that in fact these nonlinear terms can sometimes be very important and can actually dominate the dissipation in these systems. So one question you might ask is, why not do this using numerical hydro simulations? Just do a grid across the star and solve the full nonlinear fluid equations instead of doing this kind of perturbation theory approach. And the issue is that the waves can have very short wavelengths, and sort of like 1,000 or more nodes through the star, and you need something like 8 nodes per wavelength. 8 grid points per wavelength if you want to resolve a wave. And so it's just not a numerically tractable problem to do just through sort of standard numerical hydro. You really have to do this perturbation theory approach if you want to study the problems that we're interested in. Okay, so what are some of the observational constraints we have on tidal dissipation? Some of the best constraints come from observations of solar binaries. And so I guess given that there's been a lot of time that has been lost to these technical difficulties, I may end up sort of moving a little bit quicker through some of the slides than I would otherwise, because I realize people might have to go at 5 o'clock your time. So I'll just sort of try to be more brief in some sections. So this, these observations of solar binaries, you can measure the eccentricity and period in these binaries that you find in clusters of stars. And what you find is that the binaries with very short periods tend to have very little or zero eccentricity, and at long periods they have higher eccentricity. And the interpretation is that at short with short periods, the binaries are close, the tides are strong, and the tides have circularized the orbits. So for this particular cluster M35, the orbits are circular out to about 10 days or so. And so you can now do the same sort of exercise for clusters of different ages. So here's the circularization. This plot here is the circularization period as a function of age for different clusters. Here's this M35 cluster, out to which the solar binaries were circular out to 10 days. And so the older clusters have longer circularization periods because they've had more time to circularize their longer period orbits. And so then you can sort of fit this data with these solid lines, and what these solid lines are showing are the efficiency of tidal dissipation, assuming a particular value of the tidal quality factors, which is kind of like the Q of a bell. You know, how many times does a bell oscillate before its amplitude falls off by one e-folding? So larger Qs of a star corresponds to less dissipation. And so from the data, you can fit Qs of about, the data suggests that Q is about 10 to the 6 to explain the circularization of these solar binaries. They start out eccentric and then they circularize, and you need a Q of 10 to the 6 to explain the data. But then you look at the linear theory calculations, and even the most sophisticated linear theory calculations predict Qs of 10 to the 9. So they're underestimating the efficiency of dissipation by a factor of 1,000. So basically, linear theory is just doing a terrible job at explaining the data. So that sort of observation and the fact that tides can sometimes be really strong for these short period binaries motivated us to develop some of the formalism and computational tools to study tides in various types of binaries. And so in these first few papers, we developed those tools and formalism, and in the last few years, we've been sort of systematically applying those tools and calculational methods to different types of binaries. And so in this talk, I'll describe the work we've been doing on hot Jupiters, on compact object binaries like binary neutron stars, and towards the end of the talk, I'll describe the more recent work we've been doing on waves in isolated stars in which the waves are excited through internal motions in the star. And the sort of goal of this work is to figure out when are nonlinear effects important, and when they are important, how do they impact the evolution of these binaries. So particularly...
Quick, I'm so sorry to interrupt, but we have our first question,
okay.
Which is from Neela, and she asked, how do you know these are binaries? These could be multiple star systems, as the clusters look pretty dense.
So you can still, so for example, for these solar binaries, you can measure the radial velocity of the objects in the cluster, and so you know it's a binary because it has a very high radial velocity because it's a compact binary, much higher than the sort of velocity you would see in a star that's not in a binary in that cluster. So you can tell from the radial velocity, and you see a periodic modulation in that radial velocity because it's orbiting. So you know if it's a one-day orbit, you can come back half a day later and it would have be on a different part of the sine curve. Okay, so right, so one of the things that happens is when you have a tide, you can excite waves in the star. And so an important part of the story is the types of waves that a star can support. And stars can support all types of waves. I'll describe sort of the three main ones. So there's what are called P modes, which are basically sound waves where pressure is the restoring force. And so in the sun, those are waves or modes that have periods of minutes to maybe a couple of hours, but less than a few hours. There's what are called G modes. These are internal gravity waves in which the restoring force is buoyancy. These have long periods in the sun, hours to days. And then there's, if a star is spinning, you can have what are called inertial modes, where the restoring force is the Coriolis force. And those tend to have periods of order the spin period of the star. And so, here I've been giving sort of the numbers for the sun, but all types of stars support these types of oscillations, including compact objects like white dwarfs and neutron stars. And a particularly important class of modes for the tides are the G modes, the internal gravity waves. Internal gravity waves are the same types of waves you see when you throw a rock in a pond and you get those ripples. Those are surface gravity waves. Internal gravity waves are the equivalent, but internal to the star. Those are important for tides because they can have periods of days and therefore be resonantly excited by the tide. They can have the same period as the tidal forcing frequency, the tidal forcing period, and therefore be resonantly excited. So you get a situation where you have like a driven harmonic oscillator being resonantly excited. You can have significant dissipation as a result. There's a nice sort of terrestrial example of tidal resonance. The Bay of Fundy in Canada, Nova Scotia, has so this is kind of a 50-mile long bay, and the natural oscillation period of the bay just so happens to be 12.4 hours, which is the tidal forcing period due to the moon. And so, the moon is resonantly exciting the water in this bay, and as a result, there's this huge tidal range at its greatest, a 15-meter tidal range between low tide and high tide. And so this picture here is, it happens, each of these pictures happen twice a day, where all this water in this huge bay gets drained out and then comes back in twice a day because of this resonant forcing. Okay, and so you can have, many waves that are excited by the tide, but if you're doing a linear calculation, all those waves, even though you have many waves excited, they don't interact with each other. They kind of pass right through each other. They obey the sort of superposition principle. They don't interact. Whereas when you start accounting for nonlinear effects, you can have wave-wave interactions. So an important type of wave-wave interaction is what's called the parametric instability, in which you have a large amplitude, what you might call a parent wave that's directly excited by the tide. And if its amplitude is large enough, it can excite daughter waves of half its frequency. And whether that happens or not depends on how large amplitude the parent wave is, whether there are daughter waves close to half the parent's frequency, and the strength of the coupling between the parent and the daughters. But if you have this process, if you have this parametric instability, you can have significantly enhanced dissipation in your system compared to linear theory. And the reason is you have this new sort of a channel in which the energy can flow. It can flow into these daughter waves, which themselves can have very short wavelengths and dissipate energy and thermalize that energy much more quickly than the parent wave would by itself. And so you have a mechanism for increasing the star's viscosity, giving it a smaller Q, which is consistent with what the observations of solar binaries is finding, right? We need a Q of 10 to the 6, not the 10 to the 9 that the linear theory was predicting. And so in a little bit, I'll show you results in which you have many exciting waves, and you have to sort of account for all their interactions. But just to sort of give you a feel for how this works, let me start with a simplified sort of toy problem in which you have just 3 waves, a parent wave and 2 daughters. And actually, before I even show that, let me tell you what happens if you don't have the nonlinear interaction. So imagine you set this coupling to 0 and you only have a parent wave that's excited. So in that case, you have the equation of a driven harmonic oscillator. A is the amplitude, gamma is the damping rate, omega is the natural eigenfrequency of the parent, and U here on the right hand side is the harmonic forcing due to the tide. And so if initially the parent has very little energy and you turn on the tide, it'll ramp up in energy. And if I extended this plot to the right, it would reach some linear equilibrium, basically the solution to a driven harmonic oscillator. But now let me turn on the 3-wave interactions and let the parent couple 2 daughters. And what you find happens is the parent crosses some critical energy, shown by this dashed horizontal line. And when it does, it resonantly excites daughters, which grow exponentially. And so the parent, instead of reaching this linear equilibrium, saturates at basically the critical energy. And it undergoes some complicated limit cycle with the daughters, but the point is that it's a very different solution than the linear one. Right? The parent never reaches the linear energy, and the daughters, which in linear theory would essentially have zero energy, are excited to a large energy. Right? And so this can lead to a very different evolution, very different dissipation than the linear theory predicts. And so then, what you can ask is, in the parameter space of a binary, when is the tide unstable to this parametric interaction? When is this parametric instability triggered? And so the parameter space of the binary that's important is the mass ratio of the binary, shown in the vertical axis here. So the mass of the companion relative to the star, and as a function of the period of the binary, shown in the x-axis. And so anything above this kind of jagged black line here is unstable to the parametric instability. The linear solution is unstable. The linear energy is above this critical energy, and anything below it is stable. And so as a reference point, I placed a hot Jupiter on this diagram. And so what you see is that hot Jupiter has a mass of about 1/1000th the mass of a star, of our sun, and an orbital period of about 2 or 3 days. And so you see it's well into this unstable region. It's not sort of hugging this curve, it's well above that curve. And so it's very unstable to these interactions. A solar binary, which has a mass ratio of order unity, is off this diagram. It's way up here, and it would be unstable out to tens of days. And so something we realized fairly early on was that basically in almost all binaries in which tides are important, the linear approximation fails. It just doesn't adequately describe the system. And so this includes solar binaries, hot Jupiters, and compact object binaries. And so the question then is, what are the implications? We have this result that the tides are unstable to these instabilities. What are the implications? How does that impact the evolution of the system? And so let me start by describing the work that my former PhD student Reed Essick and I did in the specific case of tides in hot Jupiters. So as you can see, these hot Jupiters are well into this unstable region, and so they don't just excite a single daughter pair. They actually excite hundreds, even thousands of daughter pairs, and those daughters reach themselves very large energies and excite granddaughters, and those granddaughters reach large energies and excite great-granddaughters. You sort of get this cascade of waves that are excited in the star. So here's a result from one of Reed's calculations showing the energy in the modes as a function of time. And so his networks have tens of thousands of interacting modes. Here, we're only showing, I think, something like 1 out of every 100 modes, because otherwise it would just be a blur. What we're showing here is just 1 out of every 100. What you can see is that the energies fluctuate sort of rapidly in time, and there's sort of this chaotic kind of energy fluctuation. There's a sort of exchange between modes, and at one moment a mode has large energy, and next moment some other mode has large energy. But if you then ask what's the total dissipation in your system, so each mode contributes something to the dissipation, you can sum all that dissipation up, and that gives you this plot on the right. And so what you see is that that sort of asymptotes to a steady value. Sort of the system saturates to some nonlinear equilibrium that tells you that the total dissipation is roughly a constant. And so you can then turn that dissipation into a measure of the Q of the star, the tidal quality factor of the star. And so what we found is that Q is about 300,000 for a Jupiter mass planet in a one-day orbit. There's a pretty steep dependence on the orbital period. But this is orders of magnitude faster than the linear theory. The linear theory gives Q of like 10 to the 9, 10 to the 10. So this is telling you that the nonlinear effects are dramatically increasing the efficiency of dissipation compared to linear theory. You can talk about what does this mean for the orbital decay timescale of the planet. And what we find is that it corresponds to a decay timescale of less than about 1 billion years. So less than the main sequence lifetime of the star if the period of the planet is less than about 2 days. Whereas in linear theory, the planet would just sit there for I think it's like 10 to the 12 years. It wouldn't evolve at all. So it's really a dramatic difference when you account for these nonlinear effects. And there is some indirect evidence. You can look of orbital decay, right? You want to know how does this compare to the observables. And so if you look at the statistical distribution of hot Jupiters, how many hot Jupiters are there as a function of orbital period, you find that there's fewer very short orbital period planets than you would expect given how many there are at larger periods. And so there seems to be a clearing out of the shortest period planets. But it's kind of small number statistics. So even though there's something like 100 hot Jupiters, there's only about 10 or so that have periods less than 2 days. And so the statistics aren't great. And there's hope that maybe in the next few years with missions like the TESS space mission, there'll be many more hot Jupiters found and we'll get better statistics to measure the observed value of Q and compare it to these nonlinear predictions. But there is a really interesting hot Jupiter called WASP-12b, where we think there might be direct evidence of orbital decay. So this is a what's called a transiting hot Jupiter, a planet that's found because it passes in front of its host star and basically eclipses the host star, and we can see the slight dimming of the star as the planet moves in front. And so this is a planet with a little over a 1 day period, so very short. That was discovered a little more than 10 years ago. And it's orbiting a star with a mass of about 1.3 solar masses and an age of about 3 billion years. And so by doing what's called transit timing, you know where the planet was in 2009. You can predict where it should be in 2020, assuming that the orbital period hasn't changed. And what you find is it's not quite there. It's actually a little bit further along in its orbit. The period has decreased by something like 29 milliseconds per year. And this is observed. So there's a couple of groups who do these types of observations. And what they find is that this period is decreasing at this rate. If you turn it into a time scale, a P over P dot, it corresponds to a decay time scale of about 3 million years. And so the question then is this orbital decay? Are we seeing the period decrease because the planet's orbit is decaying? If it is, then it's the first direct evidence of orbital decay, and it's also incredibly fast, right? Because the decay time scale is 3 million years, and yet the star is 3 billion years old, and so that sort of might seem to pose a paradox. And so I'll get back to why we think that makes sense, despite the differences in the timescales. And so this is something that we thought was really interesting, and we thought about. And so in the context of whether we can explain this observation in terms of tides. And so, if you want to know whether tides are important, the first thing you need to do is understand the structure of your star. The efficiency of tides is sensitive to the structure of the star. And so from the observations, from the measurement of the temperature and mean density of the star, you can show that the star appears to be what's called a subgiant, a star that has consumed the hydrogen in its core, evolved off the main sequence, and maybe just now has shell hydrogen burning, but doesn't have hydrogen. It has an inert helium core. And so the structure of such a star for the given mass that the star seems to have is one in which it has a convective envelope and its interior is fully radiative. And so so then you can ask, okay, what is the internal gravity wave, this tide this wave that's excited by the tide, what does it do? And so you can show that it gets excited in the interface between the convective and radiative zone in the outer parts of the star. That has to do with the fact that these internal gravity waves are evanescent in the convective zone, and so their wavelengths are along there, and that's where they can couple well to the long wavelength tidal potential. So they're excited at this outer part of the star, and then they propagate inwards. And as they propagate inwards, they steepen. And that's just a consequence of geometric focusing. You're trying to put the same amount of flux in a smaller and smaller volume. And so the way that a wave will do that is by increasing its amplitude. Something like this happens in our atmosphere. Some of the atmospheric physicists in your department study internal gravity waves excited in the atmosphere, and as those propagate, they also steepen, and their amplitudes grow as they move down the density gradient. So something similar is happening in the star. And so what we found in these calculations is that the amplitude of the wave becomes larger than the wavelength. Delta R becomes larger than lambda. And so that's the condition for wave breaking. Sort of like when you go to the beach and you see waves coming to the shore, they propagate hundreds or thousands of kilometers in the open ocean, but then they come to the shore and overturn and break and deposit all their energy right there at the shore. The same thing is happening in the star. The wave is carrying all its flux through the star, and then right near the center, it's depositing all that energy and angular momentum. And so that's a very efficient, that's sort of maximally efficient tidal dissipation, because it only propagates once through the star. It doesn't form a standing wave; it's a traveling wave.
So we have another question, if you don't mind.
No,
someone asks, how about the tides on Jupiter and our solar system? There may be more observations there.
Yeah. So the Jupiter is in a I think it's something like an 11-year orbit. And so the tides are so weak due to the sun, if that's the question, that they essentially can be ignored. It's going to have a very small effect on Jupiter's evolution, unlike the hot Jupiters where the tides are very strong. There's interesting tides due to the moons. So I guess I don't know if the slide was showing that first slide, but had a picture of Jupiter's moon Io, and so there the tides in Io and the corresponding Io is low mass, so the tide it excites in the planet is weak, but the tide excited in Io due to Jupiter is strong, and so you can have significant tides there. The dynamics are a little different because it's a solid object. It's a rocky object, so you have elastic restoring forces. It's not a fluid like a star. But there's interesting tidal effects in the solar system as well. Right, and so getting back to WASP 12, you can turn this calculation of wave breaking into a dissipation in a decay timescale. And what we found in the calculations is decay timescales that are consistent with the measured value of P over P dot of 3 million years. And so we think that nicely explains that observation. There's also, as I mentioned, this sort of seeming puzzle that the decay timescale is 3 million years, and yet the star is 3 billion years old. But in our scenario that we've proposed, the star only becomes very dissipative when it becomes a subgiant. When it's on the main sequence, you can actually show that the core is convective and the wave doesn't reach nearly as large an amplitude, and it doesn't break, and the nonlinear effects are insignificant. It's only when it becomes a subgiant that you get this fully radiative interior. And it may have only become a subgiant a few million years ago. And so that sort of can explain why the decay timescale is so small, despite the 3 billion year age of the star. There's still the question of what are the chances of finding a system in this state. So the star only spends 0.1% of its life in this phase. But given the fact that there's sort of hundreds of hot Jupiters found, there's kind of a tens of % chance that we would find at least one such system. So it's maybe not surprising that we did. And so I think the story hangs together nicely. I think the only sort of remaining loose thread is whether this is really a subgiant. There's still glossed over this, but there's still enough uncertainty in these measured parameters, the temperature and density of the star, that it could still be a main sequence star of a slightly different mass. And so, to really sort of pin that down, we need more precise measurements of the stellar parameters. But that's sort of, I think, the only sort of loose thread remaining. But I think it most likely is a subgiant, and then we have a nice explanation for this tidal dissipation in the system. Okay, so let me now talk about a different system that we've studied extensively, binary neutron stars. And so these are interesting LIGO sources. LIGO is this gravitational wave observatory that probably many of you have heard about. So in the summer of 2017, LIGO made the first detection of gravitational waves from two neutron stars that merged together. And what was amazing about this event is not only that they saw it in gravitational waves, but they saw it across the electromagnetic spectrum. So they saw about 1.7 seconds after the gravitational wave signal in gamma rays with the Fermi Gamma Ray Telescope. So they saw a burst of gamma rays, what's called a short gamma ray burst. And then about 11 hours later, optical telescopes on the ground saw the electromagnetic counterpart in the optical. They saw what's called a kilonova. From this one observation, we now think that the most of the lanthanide elements are synthesized in these events. So elements like gold and platinum, which many of us have in our the jewelry that we wear. We think most of that has been synthesized in these merger events. Ones that happened within our galaxy and then formed were part of our solar system. And so, let me sort of step back and say, what does LIGO see when it detects one of these events? So it sees basically the last 3 minutes of the life of one of these binary neutron stars. So these two neutron stars enter LIGO's bandpass when the orbital frequency is about 10 hertz, which is still very fast. But over the course of those 3 minutes, the system in spirals emits gravitational radiation, which removes energy and angular momentum from the orbit. The orbit decays and it goes through about 10,000 orbits and it reaches a frequency of about 1,000 hertz. And then these two objects, solar mass objects, crash together at some good fraction of the speed of light when their frequency is about 1 kilohertz. And so LIGO has seen 2 such events so far. And the expectation is that when it reaches its design sensitivity in the next couple of years, it'll see something like 1 or 2 events like this per month. So this will be really exciting when that happens. And so, you can now ask, what about tides in these systems? So you can show that through a first approximation. You can treat the 2 neutron stars as point masses, and you'll get a pretty good estimate of the gravitational wave signal. But of course, these aren't actually point masses. They have a finite size, and that finite size means that they tidally interact as they get close together. And the tides will speed up the rate of in-spiral relative to the point mass prediction, because again, you're removing energy. You have an additional way of removing energy and angular momentum, taking it out of the orbit and putting it into the spin of the stars and heating up the stars. And so instead of maybe 10,000 orbits, you might only have 9,999 in LIGO's bandpass. And that difference of 1 orbit is roughly, LIGO sensitivity. If there were such a difference, LIGO would be able to see it. And whether you have such a difference, whether the magnitude of that phase difference depends on the detailed properties of the neutron star interior. Things like the equation of state, which we don't have a good handle on because these objects have densities that are several times nuclear density, and we don't know the properties of matter at those densities. We don't have experiments on Earth that can probe it. And so you can learn something interesting, not just about the astrophysics, but actually about the strong force and sort of fundamental physics. It also might depend on the superfluidity of the core. And so my former student, Tong Yu, and I did the first calculations of tides and superfluid neutron stars and show that they can be important. The superfluid effects can be important for tides. But most studies, just like with the other binaries I mentioned, assume that it's okay to treat the tide as a small linear perturbation to the star. But in fact, these objects are merging together. And so at some point in the in-spiral, the nonlinear effects are going to be important. And so the question is when, not whether they're important, but really when in the in-spiral do nonlinear effects become important? Is it only in the last moments before they're merged, or is it somewhere further out, in the in-spiral process? So that was the question that motivated much of our work, is when do these nonlinear effects become important? And so what we found in the course of our study is that there's a new type of instability that can occur in these systems, an instability that involves the nonlinear interaction between the tide and P modes, sound waves, and G modes in the neutron star. So this instability is very different from the parametric instability that I mentioned earlier that involves resonance between the tide and the daughter waves. This is a non-resonant instability that we don't fully understand. We think we know its threshold and how it grows, but we don't understand its saturation well. And because we don't understand it well, we don't have we can't yet predict exactly how it's going to impact the gravitational wave signal. But what we have done is created a parameterized model of the impact that we think it might have. And so there's a phase error, basically how many fewer orbits do you have because of the tides, this delta phi tide, that we've constructed a parameterized model for. And then from this signal that LIGO saw from this gravitational wave event GW 170817, we fitted our tidal parameters, this nonlinear tidal parameters, to this data, and showed that we placed sort of upper bounds on its effect. So we haven't measured the parameters, we haven't actually seen this effect, but we place upper bounds. It can't be bigger than some certain amount. But the expectation is that in the future, when we have many more events like this, we can basically stack the data in sort of in a Bayesian sense and learn, and become more sensitive to these more subtle tidal effects. And if we can do this, we have a sort of new way of probing the interior of the neutron star that's kind of complementary to other tidal effects that people have thought about. We can learn something about the stratification of the neutron star and the composition of its core, which would be really interesting. So I'll just mention briefly, something else that we've been thinking about a lot is tides in a different type of system, compact object binary system, white dwarf binaries. So these are important sources in cosmology. So they're type 1a supernova progenitors, which Sang-Wook studies a lot. And so these can understanding these systems is important for cosmology. And they're also important because they're going to be sources for a future gravitational wave mission called LISA, which is going to be sensitive to low frequencies. And so we have a paper that we're working on where we show that nonlinear effects are very important for these systems as well, their heating and spin evolution.
So I'm going to jump in with a couple of quick questions real quick.
Okay.
That have popped up in the chat. One of our audience members asked, do tides created in the hot Jupiter's atmospheres by the stars they orbit have an appreciable impact on the planet's orbital stability?
So the tides in the planet, was that the question?
Yes.
Okay. Yeah. So for these hot Jupiters, we think they're tidally locked, so that the same face is always showing to the host star, kind of like the moon is showing us its same face because it's tidally locked. And then these orbits are circular, and so there's no time-dependent tide in the planet. Right? From the planet's perspective, the star's tidal impact is steady. There's no time dependence, and so there's no waves that are excited. There's what's called a thermal tide, or there can be a thermal tide that has to do with the irradiation, and it irradiates one side, and then there's sort of a wind that can flow, and that affects the atmosphere of the planet. But that's not a sort of fluid dynamical tide. That's more of a thermal tide that people talk about.
And the second question comes from Dr. Kuntz, who's in the audience, asked, the interiors of main sequence stars and subgiants are better understood than those of giants and supergiants. Did your research yield any information about those stars?
Yeah, so I have a NSF grant that one of the projects that we're going to work on is exactly the tides in evolved stars, in stars like red giants, because as that's right, the structures are less well known, and the tidal effects can be much more dramatic because the stars are much larger radii, and the tides are very sensitive to the radius of the host star. And so one of the projects we have that we're planning to do is to study just that problem. In a moment, I'll describe not tides, but waves in red giants, and astroseismology, which people are now using to learn about the internal structures of red giants in some very detailed ways.
I think those are all the questions we have right now. So,
okay. In terms of time, do you have?
I think we started. It's 5:11 here. I think we started at least 20 minutes late, given everything that happened. So I would say, comfortably feel like you have at least 10 minits left.
Okay.
Plus, we've slowed you down with questions. So
no, that's fine. Okay, thank you. Yeah, I appreciate that. Right. So this is actually the sort of last part of my talk, which is waves excited in a star, not because the star is in a binary, but because of internal motions in the star. This is a field called astroseismology. So in the 1960s, astronomers noticed that there's sound waves excited in or propagating in the photosphere of the sun. So here's actually a real movie of a small patch of our sun. Hopefully you can see this. These sort of ripples that you're seeing are sound waves moving across the sun. These sound waves are excited by turbulent motions in the sun's convective envelope. So I'm not sure how well you can see this, but this is supposed to be like a cross-section of the sun. And so the sun, the outer third of it is convective, and those convective blobs excite waves. And those waves, although they're excited very near the surface, and we see their surface effects directly, those waves actually propagate through the entire star. And so just like on Earth, we can learn about the internal properties of Earth by studying the earthquakes that are excited at the surface, and those waves that earthquakes excite propagate through the Earth, and we can learn about the inner mantle, the outer mantle, inner mantle, inner core, outer core, through the nature of those waves. The same is true of these waves excited in the sun. And what you can do is you can do a Fourier transform of the fluctuations and calculate the power spectrum, and that's what's shown in this diagram on the right. So it's power as a function of frequency of the solar oscillations, and what you see is there's sort of discrete frequencies where you have a lot of power, and that has to do with the fact that you're exciting. There's modes of oscillation that are being excited, and that's where the most of the power is. And so by studying which modes are excited and their frequency spacing and the frequencies at which they occur at, the overall envelope where that frequency is, you can you can sort of invert the problem and learn about the internal structure of the sun. And people have done this to learn about the rotation profile of the sun, its sound speed profile, its composition, really detailed information that otherwise you have no access to. And so, for 50 or so years, the sun was really the only star that you can do those kinds of measurements in. But about a decade ago, space telescopes, particularly the Kepler space telescope, revolutionized the field. And these, so basically, Kepler had really good photometry. It was able to see fluctuations of a few parts per million, and it basically also just stared at a small patch of the sky with a small number, a small patch of the sky with just a set number of stars, something like a few 100,000 stars in that patch, continuously monitoring it, and it could see, because of its great photometry, small fluctuations due to these waves in the star and their photometric, their photospheric effects. And so one of the things that Kepler detected is waves, these astroseismic signatures in tens of thousands of red giants. And so a red giant is a star that has consumed all of its hydrogen in its core, and it has a shell of hydrogen burning, has an inert helium core inside of it, and it just puffs up enormously by factors of 10 or even 100 compared to its main sequence self. Kepler is no longer working, but this test mission is now doing the same kinds of observations. And so here on the bottom panel is a power spectrum from one of these Kepler red giants. And so just like with the sun, you can see that there's discrete places where you have significant power. There's power at, in the black, shown in black is at the for the radial modes, basically like the breathing modes of the star. You can show that there's power in the dipole modes, in the quadrupole modes, and so on. So you can, just like with the sun, look at this power spectrum and learn about detailed properties of this red giant's interior, from the frequency spacing and where the power is. And so just like with the sun, we've learned about the evolutionary state of these stars, the rotation profile, powerful scaling relations. We have direct ways of measuring the mass and radius just from these power spectra. So something that we cannot do, we couldn't do in the past, we now can do for tens of thousands of stars across our galaxy. And so sort of it's revolutionized not just stellar physics, but actually galactic physics as well, because now we have ways of measuring ages and masses and radii of stars across our galaxy. We can do what's called galactic archaeology, sort of reconstruct the history of our galaxy from these observations. And so one of the sort of interesting things that Kepler noticed is that as a star evolves up the red giant branch, as it gets bigger and bigger and evolves more and more, the amplitudes of the oscillations get bigger and bigger. And so for some reason, my mouse pointer is not moving anymore, so I can't show you. But if you look at that, I can't point you to it. But if you look at the panel at the top, the small red giants have relatively small oscillation amplitudes, and the big ones have large amplitudes. More quantitatively, that's shown more quantitatively in the bottom diagram. So oscillation amplitude in parts per million, so luminosity fluctuation, delta L over L, in parts per million as a function of the luminosity to mass ratio. And so you see that the sun has sort of fluctuations of about 1 or 2 parts per million, whereas red giants have, tens to hundreds of parts per million. So energies that are factors of 1,000 to 10,000 larger. And so that sort of got us wondering, given how much larger the energies are in these modes, are nonlinear effects important? They're sort of marginally important in the sun, but maybe they're very important in these red giants. And people have been neglecting these nonlinear effects, and again, just sort of making this linear approximation. And we think there might be some indications of nonlinear effects. So one of the puzzles that came up in these with these Kepler observations is that some stars have very little power in their dipole modes, whereas other otherwise similar stars have significant power in their dipole modes. So that's shown in an example of this is shown in the diagram, this plot on the right. So the top panel is a normal red giant, and you can see in red it has significant power in L equals 1 in the dipole mode. But the bottom panel is a different red giant, and it has very little power in the dipole modes. The L equals 1 power is almost insignificant. And these two stars are otherwise very similar mass, radius, age. And so it's kind of a mystery as to why they would have this sort of different feature, little power in the dipole modes in one and not the other. And so one of the explanations that has been proposed is that maybe in the suppressed dipole mode, there's strong magnetic fields in the core, and that star therefore has less power. The magnetic field scatters the wave, and it suppresses the amplitude of the wave at the surface. And if that's true, that would be a really interesting result, because that would mean that you would have a way of probing the magnetic field in the interior of the star, which ordinarily you have no way of knowing. We don't even know the magnetic field in the interior of our sun. And if this were true, you'd be able to measure it in a red giant, across our galaxy. But more recent observations suggest that there's problems with this magnetic field explanation. So that got us thinking, maybe it's not magnetic fields, maybe it's nonlinear damping. And so something that we're working on, again, this is a different grant that we have, a NASA grant that's going to be starting this summer, is to study mode coupling in red giants using some of the same techniques we've been using for tides, but for this astroseismic problem. And so the plot on the left is showing the mode energy, and so in black is the energy in a parent wave that's directly excited by the turbulent motions, and that energy is large enough that it excites daughters, shown in red. Those daughters grow exponentially, reach large amplitudes, and themselves then excite granddaughters, shown in blue. And so you sort of get, again, this kind of cascade of modes that are excited. And so then on the right is shown what impact this has on the energy of the parent waves as a function of time. And so the top curve in blue is what the parent would look like if you turn off the mode coupling, and in black when you allow for the mode coupling. And you see that the parent mode is suppressed in amplitude in a way that appears to be consistent with the observations of these suppressed dipole modes. And so we're doing this kind of calculation for sort of a range of red giant types, different masses and ages, to see if we can explain these observations with Kepler. Okay, so this is my conclusions. So I'll just go over these briefly, because I'm obviously well over time. So one of the sort of takeaway messages is that the linear approximation that people have been sort of assuming for a long time really is inappropriate. It doesn't describe tides in these short binaries where we think the tides are important. And so we've been sort of systematically studying the impact and showing that nonlinear effects can dramatically enhance the rate of tidal dissipation in a range of systems, hot Jupiter systems, compact object binaries, and then separately thinking about nonlinear effects in these oscillations of red giants, and showing that they can impact the amplitudes of the observed modes. There's many sort of interesting questions that remain that we're hoping to study. For example, how do you form a hot Jupiter? We think tides are important there. What's called so one of the scenarios is what's called high eccentricity migration of hot Jupiters. If someone asks me, I can tell you about that, but we think tides are important there. We think nonlinear effects are important there, and we think nonlinear effects might be important in how angular momentum is transported through stars. There's kind of puzzles in the Kepler data relating to how the rotation profile of red giants. And so we think angular momentum transport by internal gravity waves and nonlinear processes might be important for explaining some of those observations. And so, just to sort of conclude, this is, I think a very exciting area to be working in. There's a lot of really great data that exists today, and will exist new data that will come in with future missions like Plato and LISA and Cosmic Explorer, various types of gravitational wave observatories that are going to come online, follow-ups to missions like Kepler and TESS called Plato. And so I think this is going to be an exciting area for many years to come. So thank you very much for your attention and for your patience with all the technical difficulties.
Thank you for your patience. And right now, this is where everybody would be clapping, but we don't have canned laughter, canned applause ready for our live streams quite yet. But we did have one more question come in through our Q&A, and I'll ask that one. And at this point, of course, encourage anybody else out there to click on the Q&A button on the window and feel free to type in your questions now. But someone did ask, the difference between tides and gravitational waves is that tides have lower frequency, correct? Are tides harder to be measured by LIGO?
So gravitational waves are, they're separate types of waves, right? So the gravitational, even if you have 2 point masses where you have no tide at all, you have gravitational waves excited. So this is just, if you solve Einstein's equations in general relativity, one of the predictions is that, even 2 point masses will radiate gravitational waves, and that will cause these 2 point masses to inspiral. And so then the tides are come in when you imagine not point masses, but finite size objects. And so the tides that I've been talking about are just sort of fluid dynamic phenomena, that you have a distortion of the star. That distortion is time dependent. And so whenever you have a fluid that's subject to a time dependent forcing, you're going to excite waves, and those waves can dissipate. Those waves will dissipate energy and angular momentum that comes at the expense, in the tidal context, at the expense of the orbital energy and angular momentum. So they're very separate things. Gravitational waves are very separate. One of the confusions that sometimes comes up is there's gravity waves and gravitational waves, and those are completely separate things. Gravity waves are fluid waves where the restoring force is buoyancy, and so it's just sort of unfortunate that they have similar sounding names, but they're totally different from each other.
Okay, we have a number of thank yous and claps and applauses in chat. I might, while we're seeing if any other questions come in, just quickly ask, one of the big projects of NASA is the James Webb Telescope going online, hopefully in the near future. Does that mission, will that play a role at all in this kind of research? And if not, besides the missions that you're looking forward to that you list on your conclusion slides here, is there any really critical observation that you could think of off the top of your head that you're missing that you think would really fill a knowledge gap for this work?
Right. So as far as James Webb, I think it's going to for sure do very interesting things with these hot Jupiters. So one of the goals is to do what's called transmission spectroscopy. So looking at the emission of starlight coming through the atmosphere of these of the planet, and learn about the internal structure of the planet and sort of the chemistry of the atmosphere. So that might be important. It probably will be interesting for this, not for the circular systems that I've mostly talked about, but for the high eccentricity migration problem. Because one of the things we don't know is how do you form a hot Jupiter, and so we think tidal effects are important there. And so sort of in a collective sense, like the better you understand the planet and its structure, the better you can understand the tidal effects and how they impact the evolution. And so, sort of the James Webb observations may tell us something interesting and new that we didn't know about hot Jupiters themselves, and tell us about their structure, which can feed back on the role of tides and how it might affect the high eccentricity migration. So I think that might be interesting there. So new observables, new detect. I think one of the things that I'm most excited about is LIGO's future, and so LIGO has detected 2 binary neutron star mergers. It just last week went offline a little bit earlier than it was expecting.
You can also unmute yourself if you wish at this point to say hi to everybody. The live stream, so you're hearing everything I say about 20 to 30 seconds after I say it, so you might want to close that on your browser. Yeah, you gotta close the window with the actual live stream now because I'm hearing, and you're muted again.
Dan, yeah, I'm hearing like the same thing over, like every 30 seconds I get the same thing over. Yeah. I can't figure out where that is. I mean, I have like a ton of browsers open. I just, I mean, I don't know which one to close. And I hear the same thing repeated every 15 seconds.
You can start talking when you're ready. Please don't wait for me.
Okay.
And you're muted again.
Dan, yeah, I'm hearing like the same thing over, like every 30 seconds I get the same thing over. Yeah. Okay, great. Thank you. All right. Thank you, everyone. Sorry for the technical problems. Haven't used this app before and clearly didn't get it set up quite the right way. And apologies for this long delay.
I'm sorry to interject real quick. We're not sharing your projected slides, so if you could stop.
So what do you see?
Okay, I think that's it, but it's not in full screen mode, which is strange, but at least I see that it's moved.
So I can press play. Then what does it do?
I don't see any advance, no. Okay. You're good to go. I'm so sorry for that.
Oh, okay. So I'm showing full screen now?
Yes.